Now, as a second topic of today, let's consider beam and shaft problems. First, we'll consider principal stresses in a beam, okay, and it will be our first problem in the second section. And next, we'll discuss about circular shaft on the torsion combined with the bending moment. So, in the first problem, we are considering the beam. For the simplicity, let's consider a cantilever beam and try to make a arbitrary and imaginary custom error, and the cantilever beam on the bending at each interface there could be some vertical force V and moment M such that we have the moment in that direction. So the top area will be under compression and bottom area will be under tension. So in this case, when the cross-sectional shape is rectangular shape, let's try to get the normal stress and shear stress distribution out of M and B. So first, let's consider the effect of bending moment M. Bending moment M will induce the normal stress along x direction. X is the longitudinal direction as a function of y, and it can be obtained from flexure formula. And the maximum normal stress will be at the top and bottom, and C is the largest distance from the center to the top or bottom, and it will be I would say h/2 for our cases. Now, having obtained this the maximum normal stress, we can also discuss about I, which is the area moment of inertia, and it becomes 1/12 bh cube, and which is the same as ac square over 3. So that's what we obtained from chapter regarding M. Now we also had a chapter regarding the effect of V, and out of V we have shear stress along that is parallel to y direction or parallel to the plane normal to x, and t as a function of y x can be obtained as minus v q, which is function of y over it, and t is the thickness of the cross section, and t is given as b here. Okay, so from the chapter on vertical force V, we obtained the expression for qy integral. Qy integral turns out to be something multiplied by 1 minus y square, which is parabolic curve, and this gives us the information on the distribution of ty, because v and I and t, all of them are constant over the cross section. Now, having obtained the sigma y distribution and tau distribution, somebody asked us what will be the principal axis for the beam on the bending. Here, what you have to be careful is now, compared to our previous section, we are considering realistic structure, and what you can see here is if you consider this simple problem, cantilever beam on the vertical force at the tip, we have shear stress as a function of distance from the tip, which is x, and it is given as constant p. However, the moment m is given as function of position x. So what you can see here is at each imaginary surface, we're gonna have different combination of V and M. Okay, so different mixture of V and M. We're gonna have different answer at depending on the x. In addition to that, even though we have same x, depending on the y location, we can have different answer for principal axis. For example, at specific point x, the sigma can be written as minus m over I y multiplied from the flexure formula. If you plug in minus px for m, we have an I for this expression. We have 3 times p over a xy over c square. However, and which is the sigma is function of x and y. When you consider tau also is function of y after plugging in the q integral and I, and the t is which is b. Okay, and it turns out to be parabolic equation. Now what you can see here is at the top, we have because y becomes c at the top, we don't have any tau, so at the top we only have a sigma x component. So this simply becomes the principal axis. Principal axis will be longitudinal axis and vertical axis at the top of this cantilever. And if you have the consider the bottom region, it will be compressible loading and no normal stress along vertical direction and no shear stress. It will be also principal axis. Now, but in the center, at the center, when y becomes 0, sigma x becomes 0, and sigma y is 0 for this problem, and we have the maximum shearing stress, which is the pure shear stress. In that case, principal axis will be this 45-degree angle. Okay, so what you can see here is, depending on the location, we're gonna have different principal axis. In addition to that, instead of P, if you have different loading, instead of P, we can have distributed loading, and we can have some moment here. Depending on these combination, principal axis can be different at different locations, depending on the loading mode. Okay, so what you can realize from the realistic structural problem is that in contrast to our previous chapter on Mohr circle, we are considering realistic structure, and realistic structure have different combination of sigma and tau at different location, and because they have different combination of sigma and tau at different location, even our principal axis will be position dependence. Okay, and of course principal stress and maximum shearing stress will be position dependent. Next, let's consider circular shaft problem on the combined bending moment M and torsion T. Here the bending moment is applied 45 degree from the vertical axis Y, and we have torsion T, and the radius of this circular shaft is given as C. And the problem asks us what is the maximum shear stress and maximum normal stress given this combined moment M and T. Here, let's first consider like the maximum stress occurring due to each of the loading. So out of this torsion T, we can expect that the most outer area will have the largest shear stress due to T, and out of M, we can quite easily expect that along this interaxis we're gonna have sigma x will be 0, and sigma x will become maximum here and maximum here, which is 45 degree in the perpendicular direction. So to answer this question, maximum shear stress and maximum normal stress, of course they should be obtained from the Mohr circle. They are likely to occur here and there, these 2 points, because from the M, the sigma x will be maximum here and maximum here, and from T, sigma tau will be maximum along the most outer surface, and by combining these 2 locations, these 2 points will have the maximum shear stress and maximum normal stress. And what is the sigma x maximum at these 2 points here and there? So the maximum sigma from our previous lecture is given as mc over I, and I for the circular cross section is given as pi over 4 c to the 4th power, and the tau due to this torsion T is given as Tc over J, and here J, the polar moment of inertia, is given as pi over 2 c to the 4th power. Okay, so it is maximum, sigma is maximum at these 2 locations, and tau is maximum along the entire radius. Now around here and there we're gonna have pure shear stress, but after pure shear, we can expect that due to the pure shear, we're gonna have a Mohr circle that looks like this, and the maximum stress will have same magnitude with the radius. However, at this point, when we have non-zero average stress, and we have even the tau, our Mohr circle will be larger, and the maximum normal stress will be larger. So we can quite easily suspect that these are the points where we're gonna have maximum shear stress and maximum normal stress. Now for these 2 points, let's take a look at here. Yeah, this is the the cylindrical shape, and if we take a look at from the side wall, yes, this is our eye. Yeah, we are looking at here. Okay, then from the side wall, we expect sigma m from m and tau m from torsion T, and we don't have any force along this hoop direction, the y direction. So this is the our stress state with respect to x tilde and y tilde coordinate system. Now the sigma x tilde is given as sigma m, sigma y tilde is given as 0, and tau x tilde y tilde is given as minus tm. Okay, so which is obtained from the torsion T. Now, given this x, y component of normal stress and shear stress, we can obtain average stress, which is sigma m over 2. We can obtain the R, which is sigma x minus average stress squared plus tau squared. And if you plug in the expression mc over I and tc over j, and if you plug in here and here, this is what you're gonna get. And the radius of Mohr circle is given as c over j m squared plus t squared. Okay, and of course the radius of the Mohr circle will determine the maximum shearing stress. Here, to reduce this equation, I use the relationship because the I and j have same length dimension, length to the force power, but j is 2 times I. So after plugging in these relationship, we can further reduce the expression for radius of Mohr circle. Now let's plug in the values for x and y position in Mohr circle. X position, we have sigma m. Y position, along the horizontal direction, we have 0. We have to plug in minus tau m becomes tau m. Yeah, this is minus tau m our case. So if you specify large x and large y point, large x is located at some position with positive m and positive tau. Okay, and the y will be located at, because the horizontal coordinate is 0 because this is 0, and y is located along the tau axis. So after locating x and y and the center position from sigma average and 0, we can complete Mohr circle after completing this the circular shape. And what we have found is that the this is first principal stress, which is average stress plus radius of the Mohr circle, which is this, and this is sigma average, which is sigma m over 2 minus r as the second principal stress. Okay, so this is the in-plane analysis. However, we have to always worry about three-dimensional Mohr circle and think about three-dimensional Mohr circle. Okay, so when we consider three-dimensional Mohr circle, we have to consider the radial direction stress. But however, at the surface of this circular shaft, there is no shear and normal force along this side wall, so that you can immediately notice that this is a plane stress problem at the surface. So the third principal axis will be exactly located at 0. So originally we have sigma 1 here, sigma 2 here, and third point will be 0. So after completing the 3D Mohr circle, what we have found is this thing, and at least for the problem we consider the circular shaft, the maximum normal stress and maximum shear stress can be directly obtained from in-plane analysis. This is quite fortunate. So when two principal axes from the in-plane analysis is that one is positive and the other is negative, and for plane stress problem this is the case, and we can find the maximum shearing stress out of in-plane analysis only. And if we obtain the expression for tau max and sigma x, we can simply write R or sigma average, which is sigma m over 2 plus R, as an answer for our questions. And tau max is given here, sigma max is given as here, and this is what we can have as a function of the given variable. The given variable here is m and t and c, and we can write down everything in terms of m and t and c. Of course, j and I can be written as a function of c. So this will be our final answers for circular shaft problem. Okay.